Dear students, in this video I will be describing the discrete Fourier transform and the fast Fourier transform algorithm to compute the discrete Fourier transform. The discrete Fourier transform is employed for converting a polynomial given in a coefficient representation form to a point value representation form, which helps in efficient multiplication of polynomials. And the inverse discrete Fourier transform and the inverse application of the fast Fourier transform will again transform the point value representation to the coefficient representation. And as we have already seen in the previous set of slides, for multiplying two polynomials given in the given in the coefficient representation form, we are going to use this FFT and the inverse FFT along with pointwise multiplication. We'll discuss the theoretical aspects about the discrete Fourier transform and also the recursive fast Fourier transform algorithm. We'll talk about the concept of polynomial multiplication and evaluation. We talk about the point value representation and the recursive algorithm for finding the discrete Fourier transform. To understand this, we should first understand the concept of the complex roots of unity, because we are going to evaluate the polynomial given in coefficient form at the various complex roots of unity. A complex nth root of unity is a complex number omega such that omega to the power of n is equal to 1. There are exactly n nth roots of unity given by e to the power of 2 pi k divided by n for all k varying from 0 to n minus 1. The definition of the exponential of the complex number is interpreted as e to the power of iu is equal to cos of u plus I sin of u. The value omega n is equal to 2 to the power, e to the power of 2 pi I by n is the principal root, nth root of unity. The other complex nth roots of unity are powers of omega n, namely omega n to the power of 0, omega n to the power of 1 up to omega n to the power of n minus 1. Further, these roots form a group under multiplication since omega n to the power of 0 is equal to omega n to the power of n. This is a pictorial representation of the n complex nth roots of unity. The following lemmas or theorems presented without proof outline the properties of the complex nth roots of unity, which are useful in the discrete Fourier transforms. Students can study the proofs from the textbook. For any integers n greater than or equal to 0, k greater than or equal to 0 and d greater than 0, we have omega dn to the power of dk is omega n to the power of k, and this result is also referred to as the cancellation theorem. For any integer n greater than 0, omega n to the power of n by 2 is equal to omega 2, and that's equal to minus 1, and it is easily understandable from the figure which we have just seen. If n is greater than 0, even the squares of n complex nth roots of unity are n by 2 complex n by 2th roots of unity, and this result is referred to as the halving lemma. Similarly, for any integer n greater than or equal to 1 and non-zero integer k not divisible by n, summation j varying from 0 to n minus 1 omega n to the power of k to the power of j is equal to 0. As k is not divisible by the denominator is not 0, so we can have this summation j varying from 0 to n minus 1 omega n k to the power of j can be written as, because it's a geometric progression, it is omega n to the power of k to the power of n minus 1 divided by omega n to the power of k minus 1. This is the summation in terms of the geometric progression which we have here, and this, when we reduce by just changing the powers, it can be written as omega n to the power of n to the power of k minus 1 divided by omega n to the power of k minus 1. So the first term can reduce to 1, so it is 1 to the power of n minus 1, which is nothing but 0. Hence the proof. Now we'll come to the discrete Fourier transform. It is required to evaluate a polynomial a of x of degree bound n at omega n to the power 0, omega n to the power 1, or omega n to the power 2, or omega n to the power n minus 1, or we can say that the 0th complex roots of infinity and the n minus 1 complex root of infinity, and so on. Let's assume that a is given in coefficient form, a is equal to a0, a1, so on up to n minus 1. Then the y coordinates at the above mentioned nth roots of infinity can be obtained using the formula yk is equal to a of omega n to the power of k, and that will be nothing but summation of j varying from 0 to n minus 1 aj omega n kj. The vector y is the discrete Fourier transform of the coefficient vector a0, a1 up to an minus 1. Now we will come to the algorithm to compute this discrete Fourier transform, which we refer to as the fast Fourier transform. It's a method to compute DFT using special properties of the complex roots of infinity and can be computed in theta of n log n time. It is assumed that n is a power of 2. Otherwise also we can extend the coefficient representation of the polynomial to be a power of 2 by making the higher order powers, the coefficients of higher order values to be 0. The FFT method employs a divide and conquer strategy using the even indexed and odd indexed coefficients of a of x. The two new polynomials are defined as below. a0 of x is equal to a0 plus a2 of x plus a4 of x square, and so on up to n minus 2 x to the power of n by 2 minus 1. Similarly, a1 of x will be a1 plus a3 of x plus a5 of x square, so on up to n minus 1 x to the power of n minus 2 minus n by 2 minus 1. Now the original polynomial a of x can be obtained as a of x is equal to a0 x square plus x into a1 x square, and hence we will get back the original polynomial a of x. The problem of evaluating a of x at n complex nth roots of infinity is achieved by the following steps. Further, because of this, we can recursively evaluate the polynomial a0 and a1 of degree bound n by 2 at n by 2 complex n by 2 roots of infinity. So the first step in FFT is to evaluate the degree bound n by 2 polynomials a0 and a1 of degree bound n by 2 at the points omega n of 0 whole square, omega n of 1 whole square up to omega n minus 1 whole square. Combining the results as indicated in the previous equation, we can get this solution, and the solution goes like this. For a recursive FFT of a polynomial a, we first find the length n is equal to a dot length. If n is 1, return a. That will be the FFT of the polynomial a. If otherwise, omega n is equal to e to the power of 2 pi I divided by n, and omega is equal to 1. Now we can divide the coefficient vector a as a0 and a1 as shown here. First one is the even numbered coefficient values, the second one is the odd numbered coefficient values. Then we recursively compute the recursive FFT of the even numbered coefficients and the odd numbered coefficients, which we have divided as already discussed. Now this combination is the one which we are going to perform. After computing y0 and y1, we need to compute them. How do you compute? It is given in the loop from line number 10 to line number 13. For k varying from 0 to n by 2 minus 1. Notice the important thing here. Instead of going from 0 to n minus 1, we are going only up to n by 2 minus 1, because we can, from the first point calculated or the first value calculated, we can calculate the other half also. That is, if we go back to the circular representation of the nth roots of infinity, only the half of the values are going to be computed. That is, values of y at only the half of the nth roots of infinity are computed. The other half can be easily obtained using the equation given here. Yk will be equal to yk of 0 plus omega of yk of 1, and yk of y of k plus n by 2 is yk of 0 minus omega of yk of 1, because if you see the symmetry of the roots, you can easily understand this, and hence after doing that we can just return y. So that will be our what we call as the y coordinates of the different x coordinates, which are nothing but the nth roots of unity. So lines 11 and 12 combine the results of the recursive DFT n by 2 calculations, and it results like this. And the line 12 is computed, you can see this, yk plus n by 2 is yk of 0 minus of omega nk yk of 1, and this can be written as yk plus yk of 0 plus omega n k n by 2 yk of 1, since omega is you can see here, and this is because omega n of k plus n by 2 is minus omega nk, and that substitution is made over here. And once that substitution is made, I can write yk of 0 is equal to a of a naught of omega into k plus omega into k, and just by reduction it comes out to a of omega nk plus n by 2. So we can see here the equation which we are used in the algorithm gives the correct result. The vector y written by recursive FFT is indeed the discrete Fourier transform of the input vector a. Now if you want to compute the time complexity of this algorithm, you can represent that as it's a recursive algorithm in the form t of n is equal to 2t of n by 2 plus theta of n, because we are dividing the coefficient vector into two coefficient vectors of size n by 2, and by master theorem method it will be theta of n log n. Thank you. I hope you understood the fast Fourier transform algorithm and what is discrete Fourier transform. This algorithm is very important. It has applications in polynomial multiplication, in convolution of signals in signal processing, and in finding the features of an image in image processing, and many more. Thank you once again.